Hi everyone, my name is Ruochen, and I'm gonna present this paper along with my partner Kaushil. This paper is inside the social networks network, so it's about the network traffic inside Facebook's data center. First, I'm gonna say something about the motivation. Uh, the basic motivation is that designing network fabrics that interconnects and manages the traffic within data centers requires the understanding of demand that will be placed on the network by end hosts. That means when people design the physical structure or layout of the network inside data center, they need to know what kind of load, what kind of workload, or what kind of net traffic will be like inside those data centers. So the second one, physical attributes and design of network in data centers are well known, but network traffic information cannot be disclosed publicly. That means those big companies they're not willing to disclose this kind of information publicly. So the information out there about network traffic in big data centers are very limited. So next thing is many proposals based on limited workload information or assumptions of data traffic behavior may not be feasible. That's also because of the limited information available. So basically, they can only use limited information or assumptions to do their research. So their proposal might not be feasible. The next thing is about network traffic behavior in Facebook's data center can provide a different perspective in evaluating proposals and assumptions about data center traffic. So, as authors mentioned, the only data available of about network traffic in big data centers was from Microsoft's data center. So, as we know, Facebook has a very different series of services from Microsoft. So their network traffic behavior is also supposed to be different. So a study about Facebook's data center can provide a different perspective in, uh, in this kind of problem. So let's look at some background information about Facebook's data center. So they have multiple data center sites and a backbone connecting these sites. And each data center site has one or more buildings. Each building is a data center. So when it says data center in this paper, it means one single data center building. So each data center contains multiple clusters, and each cluster applies the three-tier topology shown in this figure. And as we can see, machines are organized into racks and connected to top-of-rack switches. So racks are not shown here, but we can see the top-of-rack switches. So each top-of-rack switch is connected to 4 cluster switches, and each cluster has a particular set of cluster switches. Cluster switches are connected to each other through aggregation switches called FC. So the cluster switches also connect to other aggregation switches for intra-site traffic and data center routers for inter-site traffic. So now let's look at how it works. So as we know, Facebook is a social media website, so it has to deal with those HTTP requests. So when the requests come in, first it goes to the load balancer, and then the load balancer will direct the request to one of the web servers. The web servers fetch data from the cache And if the cache doesn't have that, the server will then go to the database. Then web server also communicate with backend machines to get objects such as news stories and ads. So Hadoop nodes are not involved in serving user requests. So basically, Hadoop servers, they just do their own work, and they don't communicate with other set of servers. So now let's see how the authors get the data sources. So first one is FBFlow. So FBFlow is a production monitoring system that samples packet headers from Facebook's entire machine fleet. That means it basically is controlled by Facebook, and it will sample all the packets randomly. And this thing is comprised of two main component types, agents and taggers. FBFlow's agent process on each machine parses the headers of samples and streams certain information on to taggers. Then taggers will read part of those information and convert them and store them for further analysis. So another data source is port mirroring. So basically, the authors deployed in 5 different racks monitoring hosts across Facebook's data center network. But they can only record the bidirectional traffic for one single server in each rack. So now let's look at the results. First is network utilization. So the overall access link utilization is very low. It's only about 1%. So, and utilization rises at higher levels of aggregation, like links between top of rack switches and cluster switches. For those, utilization is about 10 to 20%, and the utilization is even higher on links between cluster switches and aggregation switches. So now let's see locality and stability. So as we can see, the upper images is for Hadoop servers. So in the 120-second time interval, 99.8% of all the traffic stays in the cluster. That means intra-rack and intra-cluster altogether are 99.8%, and 75.7% of that is rack local. That means you can see the light blue part is for intra-rack traffic. So this is consistent with the previous research. And the lower image is for web server. So as we can see, 68% of web server traffic during the capture stays within the cluster. So 80% of it is destined to cache systems. So only a minimal amount of rack local traffic is present. So we can see the intra data center. So most of the traffic is intra-cluster. That means inside the cluster. Only a small part is data center. So these two are for cache follower and cache leader. So cache followers primarily send traffic in the form of responses to web servers, and so they have very high intra-cluster traffic. So cache leaders maintain coherency across clusters and the backing database, engaging primarily intra and inter-data center traffic. So here is some traffic matrix. I'm not gonna say much about traffic matrix because it's also about it's also something about locality. So this data is from this data is from FV flow, and the previous one I just mentioned is from port mirroring. So we can see the majority of traffic is intra-cluster but not intra-rack. This is a little bit different as the previous results. So Hadoop traffic is significantly more rack local than others, but the results is inconsistent with the previous result. I'll explain later. So results for other types are generally consistent with port mirroring results. So we can see a significant different levels of rack locality between port mirroring results and FE flow results for Hadoop servers. So basically, the authors didn't explain much about that, and they also didn't say anything detail about the method they use to collect and process data. They did explain. They did set two methods about data source, but they didn't say any details about how exactly they get those data and process them. So I think the reason for this inconsistency is probably that the specific Hadoop server they picked from the rack is not quite representative. That means it might be more rack local than other servers in the rack. So we can see the results from port mirroring. The rack locality level is much higher than those from FE flow results.
Hi, my name is Kaushil, and as we previously studied that stability of data center traffic depends on time scale of observation. Now, we'll try to analyze Facebook traffic at fine time scales, and we'll try to understand various traffic engineering and load balancing approaches. As we see in the figure, we can see the packet traces of three different types of nodes and the size and the duration that they are collected in, and the three types of nodes that are web server rack, a single cache follower, and a Hadoop node. We see that Facebook's Hadoop clusters are very short. They vary substantially across nodes and across time. They also vary from one node over a relatively busy 10-minute interval, and they vary from other nodes or even the same node at different times, which reveals that there are different distributions for Hadoop clusters. We also see that even in the graphed interval, however, 70% of the flow sends less than 10 kilobytes of the data and lasts less than 10 seconds. While it is the other way around for the other types of services, which are much more representative due to load balancing, such as the cache follower and the web servers. Facebook internal service also uses connection pooling, which leads to long-lived connection and a relatively low throughput, and especially prevalent for a cache follower. Now, as we can see, most flows are active, and regardless of the flow or length, because the flow tends to be very bursty internally, and the cache flows are also significantly larger than Hadoop, while web servers they lie somewhere in middle of Hadoop and the cache flows. Let us try to understand the load balancing techniques now. Facebook's approach on load balancing is highly effective on time scales, that is lasting minutes to hours, leaving less room for traffic engineering. Traffic from various traffic from a host varies from 1 second to the next, and the distribution of the flow rates aggregated by destination rack is better if the load balancing is better. Hadoop has periods of varying traffic, and a production cluster is likely to see a lot of jobs of varying sizes. Traffic engineering schemes are leveraged by softwares like Orchestra, which relies on temporal and per job variation to provide lower task completion times, and Hedera, that provides non-interfacing route placement for high bandwidth. Largest share of cache follow traffic are responses bound for web servers. We find that the per destination rack flow sizes are remarkably stable across the web servers, and all of the flows are within a factor of 2 of their median size. Traffic leaving a Hadoop node, which we saw earlier, which is not load balanced, 90% of the traffic flows can vary in size and also over magnitude compared to the median. This stability, both over time and by destination, is because of the combination of the workload characteristics and the engineering effort that has been. Large increases in the load indicate the presence of relatively hot objects, and these hot objects are monitored and mitigated at a constant time. And a burst of request for a hot object leads the cache server to cache it from the web server, and a sustained activity for the hot objects leads to creation of a replica of the object, which can spread across multiple cache servers to help spread the load. We now move on to heavy hitters. We understand the behavior of traffic at sub-second timescales to better understand its stability. Now, what is a heavy hitter? A set of flows that we call heavy hitters represent the minimum set of flows that is responsible for 50% of the observed traffic volumes over a fixed time interval. So, the presence of heavy hitters can signify that there is an imbalance in the network performance that we can act upon. And if it's large enough compared to other flows, then that makes a difference. We can see a statistics regarding the number and size of the heavy hitters that constitute 50% of the traffic in 1 millisecond intervals for each of the 4 server classes. As we see, it is the Hadoop nodes are not that relevant because with our heavy hitter definition, the results identify themselves as 1 to 3 types of the nodes. Now, as we see from the table, rack level predictions are much more effective for both types of services, and host level predictions are much more useful for web servers rather than the cache nodes. Now, let us try to understand the implications of traffic engineering. We saw that Facebook's extensive use of connection pooling seem potential candidates for traffic engineering, although we could see that it is difficult to identify heavy hitters as we see the data centers are quite large. Traffic engineering can be done only at rack level heavy hitters, that reach the level of predictability required for either a web or a cache server. Let us try and understand the concept of switching. Now, let us try to understand the per packet features. As we could see that the Hadoop traffic is bimodal and almost all packets are either the MTU length or they are TCP-ACKs. Packets for other type of services have a much wider distribution than the Hadoop servers, and the median packet size for all of them is significantly less than 200 bytes, with only 5% or 10% of those packets fully utilized. So while we see that the link utilization is low, the packet rate is still high. A cache server at 10% link utilization is generates 85% of the packet rate, and this results that any per packet operation may still be stressed upon. Let us try to understand the arrival patterns. Benson observed that the packet arrival exhibit an on and off pattern at end host level, while we see that the Facebook data center does not exhibit this kind of a behavior even within the Hadoop clusters. Even the Hadoop clusters are not on and off packet arrival systems. And if we consider traffic per destination host basis, it's then the on and off behavior re-emerges, and we could understand that its disappearance was because large number of concurrent destinations in a data center. While significant amount of traffic is routed over long-lived pool connections, as is the case for request response traffic between web servers and cache followers, ephemeral flows do exist. Cache leaders can slightly have a higher arrival rate than followers. Now let us try to understand the buffer utilization. As we saw that we do not have a on and off traffic system in the Hadoop, and there is a high intensity flow and bursty individual flows, there is a potential increase in buffer utilization and also causes overruns. And recent development in Facebook switching platforms enabled us to gather buffer utilization statistics at fine granularity. We collect buffer occupancies over a 24-hour period for switching connectivity, web servers, and cache nodes at 10 microsecond granularity. But we saw that the buffer occupancies are non-trivial and can be quite high for web servers, even though the utilization is quite low. There exists diurnal variation in buffer occupancies and in utilization and drop rate, and highlighting the correlation between these metrics is important over time. While we see that utilization by in itself is not good for prediction of buffer requirements across different applications, a careful buffer tuning is likely to be an important concept moving forward. Let us try to understand the concurrent flows. When we say concurrent, we try to mean that it is existent or within the same window in a data center. While we find that web servers and cache hosts have hundreds to thousands of concurrent connections, but Hadoop nodes have approximately 25 concurrent connections on an average, and this goes well with the findings of Alizadeh. We can see that switches are less concerned with individual connection, but they are dependent on the destination ports. And if we group the destined hosts together, the number reduces only slightly and not at all in case of Hadoop. With the lack of intra-rack traffic, flows will traverse to an uplink port. Hence, it is important to consider flows at the rack level. Cache followers communicate with different racks. Cache followers communicate with at least 225 to 300 different racks, and the cache leaders they talk to 175 to 350. The location of the racks varies dramatically, as discussed previously. The web servers communicate with relatively low, that is 10 to 125 racks concurrently. We try to restrict our focus to heavy hitters because some switch designs employ different technologies for larger flows. We try to see that the median number of heavy hitters is 6 to 8 for web servers and for cache leaders with an effective max of 20 to 30. Cache followers, although, have 29 heavy hitter racks in the median case. Due to the differences in locality, web servers and cache followers have very few rack level heavy hitters, while a cache leaders display a different pattern. Even considering only heavy hitter racks, the number of concurrent destinations is significantly large than that which is reported by Alizadeh. For front-end clusters at least, hybrid circuit-based approaches may be challenging to employ. Now let us try to analyze the paper and see if the problem addressed in the paper. We saw that the paper studied the network traffic behavior in Facebook's data centers and compared with previous work. This is an important problem for all cloud service providers, and it can affect the effectiveness of the economic benefits of cloud computing service. The authors also referenced many previous studies to show the motivation. The importance is both theoretical and practical. So, are there any solutions? Yes, there are some previous works based on Microsoft data centers, but since Facebook's applications are very different, although we do not have access to all of the traffic patterns, the network traffic is supposed to be different for Microsoft and Facebook. The author compared all the major results with those from the previous studies and gave a decent explanation of the paper. Now, what is novel contribution or solution proposed in the paper? Since the network traffic information of large data centers is limited and not disclosed publicly, this paper provides a valuable data and information about how the network traffic will be in the data centers that serve similar purposes as Facebook, as well as how different applications and physical layout may change the network traffic pattern. How did the authors demonstrate that their solutions work? The authors generally gave a reasonable explanation for the reasons they got with the traffic engineering, the reasons they got with switching. And did the authors try to achieve what they set out? Yes, they did. Is the paper well organized and presented? Yes. Although the details about data collection and processing are not fully revealed, inconsistency of some results also lacks explanation. What do we learn from this paper? We learn that the network traffic behavior is large in large data centers is very important for designing network fabric, and it also affects the overall efficiency of the service. And there are different factors that we studied in traffic engineering and switching that also affect the efficiency. Conclusion. We saw that Facebook's data center network supports a variety of distinct services that exhibit different traffic patterns. We find that several deviate substantially from the services that we had seen in the literature, and the different applications that are combined with a scale of 10 Gbps edge links of Facebook's data center network result in workload that contrast in a number of ways than the previously published datasets. And space constraints also prevent us from providing an exhaustive account. We also studied that using end host to capture timestamp packets introduces a scheduler based variations on timestamp, and we can only capture traffic from a few hosts at a time without risking drops in the packet connection. These constraints prevent us from evaluating microbursts. They are considered as contributors to poor application performance. We also saw that packet dumps are anecdotal and ad hoc, and they rely on the presence of unused captured host and on the same rack as the target. We thus try to view the effective network monitoring and analysis to be an ongoing and constantly evolving problem and a research area. Thank you.